Okay, so welcome to the last lecture of the school. So we're happy to have Carolyn, including the condensed matter segment.
Yeah, thank you for sticking around till the end. And this last talk will have quite a bit of overlap with some of the previous talks, especially Lorenz's talk and Rob's tutorial, but maybe it will be useful to hear similar topics under different languages. And so I'll talk about these exactly solvable models or different kinds of spontaneous symmetry breaking phases of one-form symmetries representing modular tensor categories from the perspective of wave functions and Hamiltonians, and then the kind of concrete consistency equations that one would solve to derive the anion types from the input fusion category. So as you guys know, the string net construction kind of takes in fusion category, which we usually take to be unitary, and then it outputs a modular tensor category. And there's some very concrete kind of consistency conditions to derive the anion types from the properties of the fusion category. But before we go into that, I wanted to mention two things from the previous lecture that I did mention. The first came from a nice question by Matt offline, which was, in the previous lecture, we showed that for these specific kinds of three co-cycles, we had this condition on the properties of the symmetry fluxes. So this is given by describing the fusion of the symmetry fluxes. It's a three co-cycle for the group Z2 with coefficients Zn valued in U1. And then this is describing the braiding properties. And then there was this question, okay, this is gauge invariant. So you can show that if you modify this by a three coboundary, it will remain invariant. But RGG is already gauge invariant. So why do we need to take it to the nth power, right? And the resolution to this question is when you have symmetry fluxes, there's an additional ambiguity. And if you look at this paper, they call it additional kind of gauge transformation. And intuitively, you can think of this as follows. It actually pops up very naturally in the lattice model. So as I mentioned, when you have a symmetry flux, it's a termination of a symmetry defect. So the defect ends at the flux. However, there's different ways to terminate the defect line. And so, for example, you can have kind of the bare defect line and this bare termination. But a just as good termination is if you decorate each side with a charge. And so, for example, you can add an additional charge under the global Z2 symmetry at each end. You can even implement this charge by decorating this line with a circuit of Z2 symmetric local unitaries. You can just, if I have a 1D line, I can first act with ZZ on these two links, and these two links, and these two links, and then I act with poly Z operator on these two links, and these two links, these two links, and then all of the Z, there's two poly Z operators acting on each of the links, on each of the sites in the bulk, and all you have left over are operators on the left and right ends, because poly Z operator squares yourself. And this is the statement that when you have a symmetry flux, there's different kinds of symmetry flux, and that differ by charge. So as we saw in the double semi-ion model, there is an S and an S bar. And this has spin I, this has spin minus I. And from the perspective of flux insertion, it's ambiguous which one you're referring to. They just differ by charge. And so what this paper called this is like an additional gauge redundancy given by some phase And really what this phase is describing is the charge that you're decorating when you're choosing your flux termination. And so now you see here, it doesn't really matter if you're choosing S or S bar. This going to the nth power, which in this case, for example, we can take n equals 2, gets rid of the ambiguity of the minus sign. So there's additional ambiguities when you're talking about these symmetry fluxes.
Is there any constraint that the phases need to be the order of the group? Is there any constraint that the phases need to be the order of the group?
Yeah, so there's like consistency conditions on what these phases will be. So for example, for Zn, the ambiguity tells you what kind of Zn charge you can add to the end. So that's why we take that RGG to the nth power. So then it doesn't really matter which kind of flux you're choosing. Okay, and let's.
Can one? So is there also a way to say this in the language of G-crossed braided categories, where there's sort of maybe more freedom to modify a G-crossed braiding?
Yeah, exactly. So that's this gamma kind of phase that you can modify the. So there's this. As I mentioned, when you gauge the G-crossed theory, right, you have this theta and this was equal to theta AG, where this is from your G-cross category. And then there was like a ratio of 2 characters. So this guy is ambiguous up to multiplication with those kinds of phases.
And that is basically the RGG, right? The theta there.
Yeah, exactly. Yeah.
Maybe the square.
It is the braiding would be RGG squared. This is so it is additional symbol that you have in your equations. And the second remark I wanted to make was we showed that from both perspectives, from the algebraic gauging and also from the lattice gauging, you had 2 different paramagnets, H1 and H2. One went to toric code, and one went to double semyon. And so you have different results under gauging. So then you might ask, how does that tell us that they belong in different phases, right? So we said that different SPTs are in different phases. If, for example, if you look at their ground states, this has ground state psi 1 on some closed manifold, and H2 has ground state psi 2 on any closed manifold. And we say that these two are in the same SPT phase if there exists a local unitary such that this interpolation is symmetric. And so how does these two guys realizing different phases indicate that there does not exist such an interpolation, right? Well, if there was such an interpolation where these two states were related by symmetric interpolation, then all these Hamiltonian terms are local and symmetric. And as Sal mentioned, gauging maps local symmetric operators to local operators. So then if you apply gauging to everything, what you'll find is the ground state of this on a sphere is also local unitary related to the ground state of this on a sphere, because this unitary maps to also another local unitary. So then what you would find is however, this can't possibly be the case, right? Because if these are unitarily related, then the string operators of this has a certain set of string operators. And then this has the same set of string operators just conjugated by the local unitary. And it's not hard to see that if these have certain braiding properties, then these stress string operators have the same braiding properties. But we know that they don't, so they can't be related by such a local unitary. So in particular, this interpolation could also not have existed. Huh?
So why is it that if two things are related to each other by law, that not observe it, that if you take the rule of these two things, that they also related by law?
So I'm just using the fact that if this Hamiltonian consists of local symmetric operators under the Z2 symmetry. Yeah. Yeah, the symmetry is important there. Okay. So then that kind of relates the difference between the result of gauging to our original definition of SPT phases. Okay. So then let's talk about string net models. And we'll start off with wave functions. So a lot of this was already in Lauren's and Mom's talks, but we'll go through some of it again. The starting point are string nets. So a string net X is some net of strings. So you first have an input, which is a fusion category, which in the, if I'm going to use the reference the input is a fusion category. What a fusion category has is it has a set of labels. So let's call these string labels, string types. So 0, 1, 2, etc. And they have an F symbol, which is the associator. And I'm going to assume all the fusion multiplicities are 0 and 1. Okay, so this is the input pieces of data. And what a string net is, you take these labels, 0, 1, 2. So 0 is going to be the vacuum, 1, 2, etc. are the non-trivial elements of the fusion category, or what they call string types, non-trivial string types. And you can draw any diagram that consists of these bivalent and trivalent vertices. So a bivalent vertex looks like this. And so you can construct a diagram that looks like this. And you can also construct trivalent junctions, so something that looks like this. So as long as these junctions satisfy the fusion rules, which are given by these so fusion rules as you're familiar with, so maybe I should call this like A, B, C, just to match the notation. They call them 0, 1, 2, but, and then where this is for simplicity. So you can construct all possible string diagrams that are of this type. So they consist of these guys. You can even think of this as also a trijunction. And the set of such diagrams we're going to call X. To construct the ground state wave function, we can write the ground state wave function as follows. On some large disk, you can write it as follows. It's just a sum over these string diagrams, these valid string diagrams with appropriate weights, which may be complex. And how do we determine these weights? Well, these weights are going to satisfy some certain conditions, and those conditions are as follows.
Sorry, what is 1 and what is 1 bar?
This is like element of your, maybe I can call it this. Yeah. So to kind of describe this wave function, we have this complete basis of these string diagrams with their appropriate weights. But the weights will satisfy certain conditions such that you can kind of retriangulate all of these kinds of string diagrams. And so there are 5 conditions. So the first condition is that you can just sort of bend these lines. So should mention that the weight, we're going to set, kind of normalize the weight of the vacuum to be 1. So this is our first condition. Whenever I draw a box, it's saying I could have whatever string diagram outside of what I drew here. But this is how you locally simplify the diagram. The second condition, this consistency condition, is related to this F symbol. Where again we have these labels A, B, C, D, E, A, B, C, D, F. And then there's a third condition that's very similar to this, which is kind of a flipped F symbol. So it's very similar, except I'm kind of just flipping it. And you might ask, what is this F tilde? Well, it turns out that usually there will be some additional symbols. I'll explain how they're related to this input data shortly. And then there are 2 more consistency conditions. One is this guy. Space. This. And then there's a final consistency condition, which is as follows. Which is kind of this popping the bubbles condition. And here we have C, E, and AB. Okay, so now what this says is I can get the overlap of this wave function with any string diagram. And the reason is I can use all of these local moves, and I can always use these local moves to transform any string diagram to the vacuum diagram. So a simple example of doing such a thing is if you want to compute the overlap with this string state, then you can show that this is equal to basically F on this string state. And then you can use 2 Y moves to then transform this into this string state. So I didn't write down the indices, but you can figure out the indices. Yeah.
What's the meaning of just having a king labeled in number 1?
So you can think of this as this A going to the vacuum line and another A. So these are just deformations of the diagram that you're allowed to do, if that makes sense. Okay. So to remind you, yeah?
Y is same thing as N?
Oh, yeah, so I'll describe F tilde and Y shortly. But you can see here, so if you recall, I wrote down the ground states of H1 and H2. They took some simple forms. So H1 had a ground state psi 1, which roughly looked like a sum over domain wall states. And the Ising degrees of freedom. And now when you go to the gauge theory, it's the ground state of the toric code model. And what the toric code model looks like is it's a ground state, and you have a sum over loop configurations. So you have a bunch of qubits on the links, but you flip the loops, flip the spins along closed loops. So then the ground state, like this one, looks like this. You flip all the spins, but only along closed loops. So, oh, I should also have the vacuum state. So these kind of domain walls turn into loop operators acting on your state. Okay, and you can show that this is a certain branching rule where you have a Z2, so you have two states. You have two string types, a vacuum string and a non-trivial string. And the fusion rule is just that the non-trivial string fuses with itself to give the vacuum. And you can show that now if all of the different kinds of string nets, all these X configurations, are actually all of these loop configurations, right? Because if you enforce the fact that at any junction you have the non-trivial string A1, then the non-trivial string will have to just form closed loops. And so in this case, what you'll find is that this phi of x is equal to 1 for all x. And this is related to the fact that the f's and the f tildes and the y's are all 1 in this case. Now, we also had this other ground state. So if we had H2, we had Si2, and we saw that that is very similar to this state, but it had some minus signs. So this was kind of like this up state plus this domain wall state, but with a minus sign, and then plus this two domain wall state with a plus sign, and then you sum over other configurations. And you can check that the ground state of the double semion model, which you get from gauging, is very similar to this ground state. It looks the same, except again, you replace these domain walls by loops of flipped spins. So you can do this. And then we still have these minus signs, and that's indicating that there's a nice choice of gauge in which this y ABC is actually -1, or AB being the kind of non-trivial string type and C being the trivial string type. And so then what this will be is kind of this simple rule. And you can get this from appropriate choices of the f's and f tildes and y's. Okay. So to relate this back to the original input of the fusion category, what you can show is that there's always a gauge choice where you choose the following. There's a condition that you need to have, which is basically y ABC. And there's a gauge choice in which you just set this to actually be equal. The reason why we don't always allow it to be equal is sometimes there's kind of different wave functions can represent the same phase. And sometimes you have a somewhat cleaner and nicer representation of the phase when you allow for additional gauge redundancies to kind of change this y symbol. But there always does exist a gauge in which you just have this, where these are the quantum dimensions that you derive from the fusion rules of the fusion category. And there's also a gauge choice in which you choose this. Then you also have the F symbol, which is equal to the F of the fusion category. And And then you have this F tilde, which is given by so it's kind of a repackaging of the information of the fusion category in a way that allows additional redundancies that sometimes simplify the model that you have. Okay, so there's some conditions, of course. So one condition that you can immediately see is that this F symbol should satisfy the pentagon equation because the F symbol of your fusion category satisfies the pentagon equation. So there's one consistency condition that's basically something like F equals sum over F, which is your usual pentagon identity. The second consistency equation is that F tilde ABC. And all of these have nice kind of pictorial reasons why they need to be true. Well, okay, this is just basically this condition. And then the third consistency condition is basically consistency with the identity string. And then the fourth condition is also consistency with the identity string. Which I called identity string 1. Now, you can satisfy all these, and you can write down a string net ground state. But you're not guaranteed to have a Hermitian parent Hamiltonian that is commuting unless you have additional constraints.
The F symbol is 1, right? If it's allowed.
Yes. F is, sorry, this is actually what I meant. Yeah.
Sorry, but in this, it's the same star,
This does not need to be unitary in general. Yeah. In particular, even if it's unitary for some gauge, it may not be unitary for some other gauge. Yeah.
So what was enough to fix the gauge, and what was the consequence? Is just fixing the phase y and bc enough to completely fix the gauge?
No. So there's additional gauge redundancies. So in particular, even if you fix y to be this, there's different choices, like the F could be unitary in one gauge and not unitary in another gauge. And so, so you could have all this data and you have a perfectly fine wave function. But in order to ensure that the Hamiltonian that you construct is Hermitian, there are some other consistency equations, but you may also be interested in non-Hermitian Hamiltonians and not care about that. So what are the other consistency conditions? Well, one basically is that this F symbol is unitary. So if you choose to use a non-unitary gauge for the F symbol, then you will pop out a non-Hermitian Hamiltonian, which is kind of reasonable. But for unitary fusion categories, there's always a choice of gauge in which the F symbol is unitary. One sort of interesting thing is there are also like fusion categories where you don't have a choice of gauge where the F symbol is unitary. And that will give you a non-Hermitian Hamiltonian. And we heard that the string net model is a commuting projector Hamiltonian. So if you plug in an F symbol that is not unitary, you'll still get a commuting projector Hamiltonian. So you'll still get a real spectrum. But it's still non-Hermitian because the projector isn't an orthogonal projector. And those kinds of Hamiltonians have a real spectrum. They're not Hermitian. So I guess they secretly inherit some PT symmetry of some type. So for example, if you want to look at the Galois conjugates of topological phases that admit gap boundary, then you'll find string net model Hamiltonians that are not Hermitian, but still commuting projector.
Is this a fact that's proven for all like non-Hermitian F symbol? Like if you have non-Hermitian F symbol, then you always have like non-Hermitian Hamiltonian. Is this like proven or is it like observed, believed to be true?
There might be special cases, but there's basically 4 conditions that maybe I won't write down because I've already written down a lot of conditions. But there are 4 additional conditions that you need, one of them being the F symbol is unitary. And if you don't satisfy all 4 of those conditions, then you can't guarantee that the Hamiltonian you write down is Hermitian. And so for those Hamiltonians that are not Hermitian, they sort of have an interesting property where like this wave function you write down might have algebraic correlations. So it's not even, so those types of wave functions, I mean, they're still a perfectly fine wave function, right? So you might ask, okay, you have a non-Hermitian commuting parent Hamiltonian, what does that imply? So it turns out that those wave functions are still valid wave functions, but they are the ground state of some gapless Hermitian Hamiltonian. So you could have some non-Hermitian Hamiltonian that has some set of left and right eigenvectors, and they're bi-orthogonal and have like fast decay of correlation. But if you just took correlations in left and right alone, and left is kind of what you would get from this construction, then you would have to have algebraic decay of correlations that would indicate any parent Hamiltonian that was Hermitian would actually be gapless.
On the second line, is there a B missing?
Sorry?
And on the second, this is the condition. Like, yeah, is there a B missing?
This is A, B, C, D, E. Yeah.
What about the PT symmetry comment that you made? Is that also something that's in the literature? That they're looking at a non-unitary case where it's real spectrum? Because that seems special, right?
Yeah, so I don't know how understood this is in the literature. So all I know is that if you go through the string net construction, you'll still get a commuting projector. And because it's a projector, it has eigenvalues 0 and 1, so it has to have a real spectrum. Now, how to relate the existence of such a real spectrum to the existence of some antilinear symmetry that squares to 1, I don't know how to do in general. It sort of like makes sense because the non-unitary minimal models also are PT symmetric, but I don't know how to like directly go from that observation to like some PT symmetry possibly of the Hamiltonian you get from the string net construction.
So if I think the literature is proving PT symmetries are equivalent to pseudo-Hermitian, and pseudo-Hermitian is necessary for it to have like real spectrum. It's not proven to be equivalent. But there's also something called OO dagger pseudo-Hermitian. So if you're OO dagger pseudo-Hermitian, then your guarantee is to have real spectrum. And it's proven, and the proof is actually pretty easy. The paper was only like back 5 pages.
Yeah, certainly if you have PT symmetry, you can spontaneously break the PT symmetry and have eigenvalues in complex conjugate pairs. So it doesn't guarantee a real spectrum. But because this has a real spectrum, I guess there's some sort of PT symmetry hidden in there.
Are the phi of x weights, are they integrated under this?
No. Yeah, so as I mentioned, if you're looking at the double semyon model, there is a convenient choice of gauge where you actually modify this y, a, b, c to not just be this guy, but has a minus sign. I think it's sort of similar to like absorbing the Frobenius-Schur indicator into dimensions. That is the particular choice of gauge that gives you one wave function. You can choose some other choice of y with appropriate gauge transformations. In particular, you can choose this where y is always positive, and that will give you a different wave function. But you can have many different wave functions that realize the same phase, right? Because like as long as they're related by a local unitary transformation, they realize the same phase. So so indeed, this weight is not independent of navigation. Okay, so to summarize what we did, we have an input fusion category, and then with this fusion category, we can draw all of these string diagrams. And then the string net ground state lives in this string Hilbert space consisting of states that satisfy these fusion rules, these string diagrams. And because it can be constructed out of all that states, all you need to do is specify the weights. And what these weights allow you to do is you can, and then with these weights, you have all these consistency conditions that are compatible with the input fusion category, so that given any complicated large string diagram on some very large lattice, you can always simplify to the vacuum and then compute the weight. Okay. And so this gives you a well-defined kind of wave function, there are some gauge redundancies, but any choice of gauge should realize the same phase. Okay.
So that, will that be a very infinite sum if you write down the state?
Yeah, because so for example, if you have some pi-valent lattice, right? Even for this guy, you have a string diagram that's like this loop. And you have a string diagram that's like this loop, and all the other loops that you can draw. So it's a very large sum. But so yeah, you have to normalize it appropriately, but it's can
I
still.
think of it as living on a lattice which is finite, so that actually is a finite sum in the end, even though it's large.
I don't see. So I do think about it as living on a disk
Okay.
with like a smooth boundary,
Okay.
and then any kind of string diagram should be simplified. So there shouldn't be anything that goes wrong as you increase the system size. So there's kind of a canonical gap boundary of this string net, which is a so-called smooth boundary. So you consider the system on a disk, and you can show there's a unique ground state on that disk. Okay. So the construction of the Hamiltonian was kind of already discussed, but I'll just quickly review it because it will be related to how we determine the anion types, or the elements of the modular tensor category from the string types. And so, as was already in the tutorial from this morning, the Hamiltonian, I'll use a little bit of different notation, but it's kind of the notation that they use in the paper. Oh, and maybe just as a fun fact, these kinds of non-unitary TQFTs were actually, there was interest in them from a long time ago from the fractional quantum Hall community, because there were kind of proposals for states called like the Gaffnian state that turned out to be, I think it was a something related to a Galois conjugate of the Fibonacci theory. And so then people were interested in whether or not this is actually like the ground state of a gap Hermitian local Hamiltonian. Turns out that there's some rigorous proofs that it cannot be. Okay. And it's kind of conjecture that that's true for any such non-Hermitian version of the string net. Oh, another kind of cute remark is, so maybe I should talk about this at the end, but string nets kind of, you might ask, what kind of phases do they realize? So certainly you need a gap boundary. So in particular, that means that the chiral central charge is 0, but there's other constraints. And more recently, some people have formulated those other constraints in terms of higher central charges. Some of you are familiar with that work. And so the chiral central charge is related to like dA square e to the I theta A. But you can also have the higher central charges where you basically take this theta A to the nth power and then appropriately normalize it so it becomes a phase. And so there are also obstructions to gap boundary given by non-trivial higher central charge. And there's some nice work on that in both the math literature and the physics literature. One interesting thing is you can show that there's a procedure that I kind of briefly mentioned called Galois conjugation that changes the braiding properties of your modular tensor category, but preserves the fusion properties, and you can show that that maps the higher central charge of a certain theory to a chiral central charge of another theory. The other theory is sometimes not unitary. So in particular, it can violate, like, it can be a string net model where this is not, doesn't have a unitary gauge. But at least this says that if you map the high center charge of this unitary theory to the chiral center charge of this non-unitary theory, this non-unitary theory still has a commuting projector Hamiltonian. So it seems reasonable that like that's should also be 0. And so that gives some evidence, physical intuition for why these higher center charges should be 0. And it's conjecture that they sort of realize all phases that have a gap boundary. Yeah.
I believe higher central charges, if you have a TFT of a computer, like putting it on like funky net spaces or weird angles. So how do you compute it with this lattice theory?
So the higher center charge, you can compute it in that way, but you can also just compute it using the algebraic data, right? And so once you have a lattice model, you have the algebraic data, which I'll mention shortly. Okay. Okay, so as was discussed in the tutorial this morning, these two terms of the Hamiltonian have very simple interpretations. So what the QV operator does is it takes any configuration and it ensures that the string diagram basically satisfies the fusion rules. So for example, this. Where I've, again, just simplified the fusion to have n ABC is 1 or 0, just for simplicity. So this is saying that delta ABC is going to be 1 if this n ABC is 1. So this is basically n ABC. So it's just 0 or 1. So I'm just writing delta because we're only considering cases where 0 or 1. So this just kind of projects onto, this is eigenvalue 1, or states that satisfy the fusion rules of your input fusion category. And as was also mentioned this morning, this BP also has a simple interpretation. It's just taking kind of one of these plaquettes and it's inserting all these different strings. So in particular, you can write BP as follows. And what BPS does is it inserts one of these strings. So, yeah. And so this runs over elements of your fusion category. This just comes from data of your fusion category. And what this BPS does is it inserts a string of S. And then you can use all of these Y's and F's and F tildes to basically absorb this guy into your diagram. So for example, the first step you might want to do is you kind of absorb with a bunch of Y's into these edges. And then you can use a bunch of F moves and Y moves to fully absorb this. So then this will be a sum. So if this is kind of like E1, E2, E3, E4, E5, E6, let's call this E R1, R2, R3, R4, R5, R6. So all of these E's and R's have n values they can take, where n is kind of the number of string types. Then this will change into E1, E2, 3, E4, E5, E6 time of these diagrams. So it only kind of modifies these 6 internal legs. And then you have the same R labels. So the intuition is this QV projects you into this. Oh, and I should also mention that this BP is kind of conditioned to only be non-zero in configurations that satisfy Z fusion rules. So you can think of this BP as being multiplied by the QV. So the intuition for what this is doing is QV takes you to this stringnet Hilbert space, this set of states that satisfy all these fusion rules. And then this BP is giving you fluctuations. So if you just had a single kind of these configurations, of course, this Q, maybe I should call this QI. This QI acting on that will be satisfied. It will have eigenvalue 1, it's a projector. So if your Hamiltonian only consisted of these QIs, any kind of string configuration will minimize your Hamiltonian. However, if you want your wave function to be not just a single string configuration that satisfies the fusion rules, but a big coherent superposition of all of these configurations with appropriate weights, then you need this BP to kind of fluctuate you. And so this is actually kind of the opposite of the quantum double. So some of you might be familiar with, there are multiple different exactly solvable models for topological phases. One class being stringnet models, and one class when you have like a G gauge theory being quantum double models. And in quantum double models, they actually look a little bit different. So they're more like the toric code that we introduced many times. So quantum double models have a vertex term and a plaquette term on a square lattice. And so in the quantum double model, as we saw, the plaquette term is kind of a zero gauge flux, so it's a constraint. Whereas the vertex term was giving you fluctuations because it's giving the group action on the links. And so on the other hand, for the stringnet model, the vertex term is giving you the constraint, and the plaquette term is giving you the fluctuations. So there's kind of a swapping of between the quantum double and the stringnet model. So for example, if you construct the so-called rough boundary of the quantum double model, that actually corresponds to the canonical smooth boundary of the stringnet model for vec G. Okay. Now, it's, if you just make these assumptions and also the other 4 assumptions that I didn't list to ensure that your Hamiltonian is Hermitian, it's still hard to see that this is commuting. And so it takes a lot of lines of algebra to show that these QVs and BPs are actually commuting projectors. In particular, it's quite difficult to show that these BPs on different sites commute with each other, because like each of these is supported on this big kind of plaquette. So neighboring plaquettes have the possibility of failing to commute with each other. And it's actually quite a lot of work to show that they actually do commute with each other. So that's a commuting projector Hamiltonian. It has a unique ground state on this disk with the canonical smooth boundary. And that ground state you can show is given by this ground state. So the input is a fusion category. You construct a wave function, and then you use the wave function to construct a Hamiltonian. Why is the ground state this wave function? So now what we want to show is that this guy we want to show that this guy minimizes the Hamiltonian. It's easy to see that it minimizes all of the QIs, right? Because each one of these x's satisfy by construction the stringnet constraints. So it's easy to show that it minimizes all the QIs. And now to show that it also minimizes the BPs, you just need to show it's a projector, so you just need to show that BP acting on any stringnet configuration acting on this state gives back itself. So it's an eigenvalue 1 under the projector. And to show that is not too hard because we know that this BPS kind of inserts this S string. And so what you can do is you can use kind of this Y move then to say that this is equal to Y So in particular, BPS acting on any x is equal to YSS1 x. And now you can just use this guy, you can actually choose this guy to be the dimension. So Y, S, S, Y, S, S. And now when you sum over all of the S, you get a sum over the dimension square, which cancels with the sum over dimension square in the denominator, so it gives you 1. Okay, so good. We have our wave function, which is just all of these string nets that you construct from your fusion category with appropriate weights. We construct a Hamiltonian. And then the question is, what is the phase described by this Hamiltonian? So what are the anion types? And how do those anion types relate? How do you derive those anion types from the input data, which is the F, F tilde, and the Y's? So there's kind of an ansatz for what we want these anions to do. And as Sal mentioned, these anions are topological in the ground state. So this is a tensor product Hilbert space. So you don't have any tight constraints, but we want them to act topologically on the ground state. So to get the anion types, we're kind of looking for string operators that act topologically on the ground state. So you also have this condition. So if these two are the same points on the left-hand side and the right-hand side, you can deform the string in between them. So this is what you want. You want to find operators that act on your ground state and are topological. And so you can take kind of an ansatz for these operators, these line operators. And the ansatz is that we're gonna, so each of these anion types are gonna be labeled by some pieces of data. So let's call these anion types alpha. And there's going to be kind of 3 pieces of data. So there's an omega symbol, omega bar symbol, and a list of integers. So this is a list of integers. This is shorthand for a list of integers. That take value. So for every string type that you start off with, you have an integer. And this is kind of saying that my anion is kind of built out of these string operators, or these string types. The physical intuition of what's happening is these integers tell you what the anion becomes when it approaches the canonical smooth boundary. So as we mentioned in the previous lecture, for example, if you have the toric code that was a rough boundary because you were using the quantum double. But basically, if you have some gap boundary and you have a kind of canonical Dirichlet boundary condition, there are some line operators that end. So for example, the E line can end topologically. The charges can end topologically on the Dirichlet boundary conditions. But then there are other anions. So for example, the flux in the Z2 gauge theory does not end. And so the flux becomes an excitation near the boundary. And so there was an identification of E goes to 1, 1 goes to 1, M goes to M, and EM goes to M. This came from a VecZ2 fusion category with trivial cocycle. VecZ2 has 2 elements. So this allowed us to map our 4 elements, which were the 4 anion types, onto 2 elements. So when you bring anions to the boundary, there's a mapping between the anion types and the boundary string types. And so you can think of this label basically as what would this anion become if you brought it to the canonical boundary. So for example, there will be a set of anion types that contain the trivial string, the vacuum string 1. And those are the anions that will belong in the canonical Lagrangian algebra, which describes the canonical gut boundary of the stringnet model. But there will be many other anion types, and there isn't like a very, in general, here there was kind of, a very clean delineation, but there's often the case where like you have an anion type that contains many possible strings. So the Fibonacci is one such example, the double Fibonacci theory. Okay, so this is kind of a multiplicity. The terminology is a bit confusing because you have these string types, they call them string types, and you have anions, but they call them string operators. But I'll call them anion line operators to kind of not confuse them with the string operators of the input fusion category. Yeah.
Is it possible to have multiple line types that don't come from the whole anions? Is that possible?
Sorry?
Is it possible to have anions on the boundary, Dirichlet boundary, that don't come from the bulk, that come from that confined?
Yeah, so here you see that these map onto elements of VecZ2. So there are 2 elements of VecZ2, right? So the ones that are not condensed, so any gap boundary, you have a set of condensed anions and a set of confined anions. And so you can kind of cleanly split them, map all of them into condensed or not condensed. So they either map onto like some, in this case, they either map onto the non-trivial element or the trivial element. Okay. So this tells you like the multiplicity of the string type that is building up the anion of interest. And these symbols are kind of symbols that you need to solve in order to ensure that this anion type can actually, this anion operator can move topologically in the ground state. So for example, what we want to say is, this is kind of the picture that you should have. And this was already kind of the picture in Lawrence's lecture, where he had the string diagram, and you have, which are built out of the fusion category elements, and you have another string, which is basically the anion type that's moving between in that diagram. And so for example, you want to have, so something like this. Suppose that we had some string diagram. So these are all labeled by elements of your input fusion category. And then you want to act with a line operator along some path. And let's suppose that the path kind of looks like this. Maybe I should use it. The path kind of moves below the strings. And so what this does is it kind of gives you a sum. It inserts this anion string alpha. And this anion string alpha consists of many different of these other string types, but you can now kind of fuse this into your original string diagram and try to ensure that this is independent of where you put the string, of where you put the anion line. But this is the basic picture. So this anion operator consists of many strings, and they create excitations only at the endpoints, and they act on these string diagrams by insertion of this line. And then you can decompose that line into the string types, and then you can just have try to ensure that this line can be fused in a way that leaves that is topological and independent of where exactly the line is drawn. Okay, so for example, so to ensure that you can do this, I'm just going to tell you what these omega symbols are. So the ways that you can simplify these diagrams are using these kinds of deformations or simplifications. So all of these, so the alpha, of course, is your anion type, but all these other labels are just from your fusion category. And so you can have this omega symbol, which tells you how to simplify this diagram, where you've put the anion operator under the original string. This is kind of a convention. You could have also done it over, but the convention of the string net construction is you insert the anion line under all the strings of the original diagram. So the second kind of omega bar is defined in a somewhat similar way. Oh, and I should mention that these indices, the sigma r and sigma s, take value in n alpha s r and n alpha s. So, for example, if this is, I don't know, 1, then these are, there's only one element, but then if this is like 2, then this is a bigger matrix. So this is some rectangular matrix whose indices take value in these n alpha s and n alpha r. Yeah?
How do you come up with the requirement that, like, you want these anions to be able to braid with your string types?
Yeah, so that will come up shortly. So as we can see, we can simplify any of these diagrams with the insertion of an anion to just a string diagram, right? And then that will come with some amplitude. So for example, then what you can do is you can compute the braiding, as I will mention shortly. You can compute like the braiding by computing something like and this should compute the S matrix element. And now you can simplify each of these diagrams into just some amplitude, some number, right? Because this is going to insert some string type. You then simplify so it becomes just some wave function with some weights in the string net Hilbert space. You take the overlap, and then you take the overlap in the denominator. That will give you some number, which is the S matrix element. Okay, but we'll go to that again shortly. So this is the definition of omega. There's a somewhat similar definition of omega bar. So the definition of omega bar is something like this. So again, there's a simplification. And in particular, you can actually, when you're trying to find solutions of these guys, there's some simplification. So for example, this is only going to be non-zero if A and R confuse to B, and if S and A confuse to B. And this guy is only going to be non-zero if R and A confuse to B, and A and S confuse to B. So this is a fusion category, so it's not necessarily abelian. So these are not necessarily symmetric. So for this guy, this is kind of has a delta function. And this similarly has a delta function. So it's only going to be non-zero if these, first it's only going to be non-zero if n a alpha r and n alpha s is both non-zero. And it's also going to be only non-zero if as confused to b and ra confused to b. Okay, so then now what you want to do is, this is how you simplify the string diagram once you've inserted the anion type. And then that means that whenever you have any string insertion, any anion insertion, you can always just simplify it back into your string net Hilbert space. Yeah.
So what are the subscripts that you make?
The sigma r and sigma s, this is like some rectangular matrix, and the sigma r and sigma s are indices of that rectangular matrix, taking value between like 1, 2, 3, up to n alpha r and alpha s.
Do they correspond to anything on the diagram on the rightmost graph? Is it like counting?
Yeah, well, the idea is that this anion alpha, there should actually be alpha here. This anion type alpha decomposes into the different string types. And so then there's only going to be a decomposition where it includes a string type S and a string type R if n alpha R and n alpha S is non-zero.
That's fine. But sigma r and sigma s then are just numbers associated to...
They're like the indices of this rectangular matrix. Yeah.
I see.
Okay. So this tells you how to sort of deform this anion insertion into how to insert this anion onto your wave function. And now we just need to show that it's topological. So to show that it's topological, it needs to satisfy, there are again consistency conditions. There are 3, so that's not too bad. So one that you need to solve is basically you need to ensure this. So this is just allowing you to deform in one direction, and then setting it equivalent to something like this. So this is one thing that you want to make sure that everything is topological. And if you work out the equations that this implies, then you get something that looks sort of like the pentagon equation. So you get something that takes something of this form. That's kind of the consistency condition that arises from requiring this on your wave function, on your string operator, on your anion operator. Sorry. The second condition is something like this. So it looks somewhat similar. And then you have one more condition. so if you have all three of these conditions satisfied, then that kind of ensures that you can move your anion operators topologically in this ground state wave function. And so what that leads to is it leads to three equations that you need to solve. One being this guy, and then the other two equations are somewhat simpler. And so this means that given an input fusion category, so this is the F symbol of your input fusion category. And then you have all of these guys, omegas, that are determined by F, F tilde, and Y. And then you can solve for consistent solutions to this guy. And what you can show is that, like, if you have two solutions, you can always take a direct sum of them. So if you have two solutions for these omegas and the n's, then you can always get another solution by taking a direct sum. In particular, you have to be careful because you can have multiple anions that have the same n alpha s but different omegas. But if you have two solutions for omega, you can always do omega A with omega alpha, beta, and then n. This will always be a solution as well. So you're kind of looking for the irreducible solutions. And so then the procedure that one would take is you would consider all of the possible ways to form an anion out of these input string types. Then for any given set of labels, n alpha s, you look for the different kinds of independent solutions of these omegas. And that's something that you can do for simple models. You can also, if you don't really know how to use a computer like me, you can also even do this for Zn times Zn Tumbar Yamagami, and it's not too terrible to solve these equations. Okay.
Do people study, so I understand you're studying ground states and stuff. Do people study excited states in these models and try to sacrifice some of these rules in some way? Is that something interesting to do? Or?
Yeah, good. So one of the useful things about having a lattice model for a topological phase is you can put it on a computer. And so there are two, maybe, examples. There's probably many more, but I know of a handful of papers where people can even study transitions, confinement, deconfinement transitions for non-abelian topological order. So one example is like double Ising to trivial or double Fibonacci to trivial by tuning parameters in kind of a stringnet model. So for example, you can first have a Hamiltonian that is just your stringnet Hamiltonian. And then you can try to tune a phase transition where you just go to the string diagram. You want all the strings to just be the vacuum string. And that will give you a trivial phase. So you can try to interpolate between those two states. And so that's one way in which people have tried to tune the confinement transition from doubled Ising or double Fibonacci. And then another reason why, and I think it's kind of interesting because as someone asked yesterday about how much we know about these confinement, deconfinement transitions, and I would say we don't know very much. So in particular, we only have some few numerical results about the second order, and they seem numerically to be second order transitions between doubled Ising to trivial and double Fibonacci to trivial. But I don't know much beyond these numerical results. And one sort of interesting tidbit is when you have non-abelian anions, as you know, as you create more and more of these anion excitations, if they're far separated, then you have a degeneracy from fusion space. And so you might expect that as you try to tune a transition by creating more of these excitations, you get a very high low energy density of states. And so in these two papers that I've seen try to tune through this transition, they found a very high specific heat exponent, like very large. I think it actually saturated like the unitarity bound. If you look at kind of what you would get like constraints just from conformal symmetry. Yeah.
And what's all these two references?
I don't have them off the top of my head, but I can give them to you later. Yeah. So I think it's kind of interesting open problem, like what do the transitions look like? Are there qualitative differences when you have transitions driven by non-abelian condensation versus abelian anyons? For example, if you always have this phenomenon of like very large specific heat. Another modification that is maybe related to the question that you asked is in this kind of string net model, it's very easy to create excitations of your plaquette operator, because you can create excitations of your plaquette operator while staying in the string net Hilbert space. However, if you want to create excitations of this QI operator, then you have to leave the string net Hilbert space. And so people kind of use these string net models and try to understand properties of string net models under noise and decoherence and things like that, and how to error correct the noise. And so they're very useful tools when one is trying to construct decoders or these topological phases under noise. And so it's a bit tricky to get out of the string net Hilbert space. So one thing that people have done is you have this original hexagonal lattice that your string net model lives on. And one thing that people have done, I think Frank was also involved in this, was if you don't want to get out of your string net Hilbert space, you can sort of add these like flags. This is called the so-called like extended string net model. And so if you have a violation of the fusion rules at this vertex, you can sort of move it to this kind of flag degree of freedom. So then at the end of the day, all the fusion rules at all these trijunctions are still maintained from your fusion category. And this is a way to kind of keep track of those errors while staying in the string net Hilbert space. So there's some extensions that people have done along these lines that, especially in the study of like decoding and error correction. Because, yeah.
You mentioned that the computation of these omega explicitly, you know what it looks like for these combined graphs.
Sorry?
You mentioned that these string operators, they can be computed explicitly in specific cases where it's more general. Is that also combined graph?
That also in, sorry, in which I can do it?
In that case, compute explicitly what these
Oh, these guys.
No, the string operators, the whole phrase.
So you're asking whether or not I can get an operator form for the anion line operators?
Basically asking, can you export omega that you have before?
Uh-huh. Yeah.
In what cases do you know that?
So in this paper here, okay, so I think that there are two, so in this paper here, they gave several examples. They gave the example of Z2 and twisted Z2 gauge theory, Z3 gauge theory, which is no longer, and twisted Z3 gauge theory, which is no longer time reversal symmetric, so that's kind of an upgrade. String net models don't need to be time reversal symmetric. They also computed it for Z3 Tambar-Yamagami, so they have the omegas for Z3 Tambar-Yamagami. And Fibonacci, doubled Fibonacci. And and probably other papers, people have computed this omega more generally. So I also was looking at this for Zn times Zn Tambar-Yamagami. And for the purpose of computing topological spins, you don't need all of the omegas. You only need certain omegas. So it's not too hard to compute the omegas in that case either, because there the F symbol has a rather simple structure because it's just this bicharacter and Farbini-Schur indicator. So when the F symbol is rather simple, then then you can plug in those F symbols, and it's not too hard to get solutions for these omega matrix elements.
Do you know how people solve this in general? Because schematically, for instance, schematically, you can use a schematic thing of arbitrary positions or representation theory of two elements. That's schematic.
Yeah, well, I wrote in my notebook, and yeah, but I mean, okay, yeah, you can probably write down a code that can try to solve. They're nonlinear equations, so they're kind of hard to solve.
If you frame it as a representation theory of Q lambda, actually totally new. So it looks nonlinear, like you can linearize it, but then the way to solve that is directly, but you can get arbitrary precision, which is as
Yeah, because you're saying like numerically, you might not get the rational numbers. You'll just get approximations. Irrational numbers, you'll get.
You get 50 digits of precision for square root.
Okay, that takes some insight though, right? So.
A little bit, but I was just curious what sort of thing, to what extent people know about these things now.
Yeah, I don't have a good understanding of the numerical tools people use to solve things like this. I would imagine that if you have efficient numerical tools to solve these kinds of consistency conditions, you can also have efficient numerical tools to even solve more complicated things like MTC data. And certainly that's a hard problem. And so I think maybe these are also hard. But maybe you probably know more about that than I do.
We have tools for solving this empirically, so I'm interested in what would that imply when you're computing MTC data.
Yeah, I will say that like even if you solve for these anion line operators, that doesn't give you F and R symbols. So one kind of aspect of the string net construction is you really only have access to closed string operators, because these kind of closed string operators you can just deform into your string diagrams. You don't really have access to open string operators because there's ambiguity of how to truncate these anions. And so if you want to look at things like F and R symbols, then you have junctions. So you need to choose terminations. So in all of this construction, the easiest thing to get is actually the gauge invariant data, like rating properties. And there's no formula. For example, you might be like, oh, I want a formula for the F and R symbols of my MTC given the data of my input fusion category, and there's no such formula. Because like you might want that, oh, now that I have a solution for these omegas, can I get F and R symbols? And there's no formula. And you kind of, in principle, you can be like, oh, once I have the anion strings, I can terminate them, do these F and R moves. But yeah, there's no canonical way to really define the junctions yet. Maybe that's something that people can work out. But.
Yeah, well, maybe complicated, but I think I sort of know how these things work out. So.
Okay, yeah, maybe.
Just seeing how useful that is.
Okay, so there's a couple minutes left, so maybe I can just. So the idea is you get these anion by getting solutions for these string types, and then for each set of these string multiplicities, you find solutions for these omegas, and then you choose the irreducible ones, and those are going to be your anion types. And then from this, you can sort of compute properties that you might want. So as I mentioned, this is like S alpha beta. And there's very explicit formulas. So you can write S alpha beta. So you can write this for the S matrix elements just in terms of the omegas. And then you can also get the topological spin. Where d alpha kind of naturally is something like this. So sometimes if you just want to compute topological spins, once you have a solution for these omegas and these n's, then you just can compute these guys. Okay, so this is kind of, just to finish, maybe I can touch on some examples. So as I mentioned, the torque code and the double semion are examples where this function 5x is rather simple. It's just plus or minus 1 given properties like the number of loops in your string diagram. And the interesting thing about the double semion case was that it was kind of convenient to choose a non-canonical, like choose a gauge choice where this y was not positive. But
sorry, Carolyn, in that formula for Pita, what are the indices on the omega, S bar, S, and then S prime? In the formula for theta,
yeah.
What's S prime?
Oh, sorry. I probably. This should be SS1. This is a vacuum string.
Okay.
And just to give you a flavor, so for example, if you put in the Fibonacci fusion category, this was already the example in the tutorial this morning, then you have 4 anion types. And so then you can consider n alpha 1 and n alpha tau. I'm gonna maybe put this tau as tau tilde because this is the tau label of the string. This is the Fibonacci anion type, so I don't want to confuse them. And so you can show that this guy has 1, 0, and these guys have 0, 1, 0, 1. But these guys have different solutions for the omegas and omega bars. And then this tau tau bar has 1, 1. And the fact that these both have n alpha 1 is non-zero indicates that the canonical Lagrangian algebra is 1 plus tau tau bar. And that's because now when you bring this tau tau bar to the boundary, it has part of it becomes the trivial string. Okay, that's kind of all I wanted to say in terms of string net models and Hamiltonians. As I mentioned before, there's some subtleties because we don't have at least in this in the original paper about string net condensation, this updated paper and other papers I read, there wasn't like a nice way to get FNR symbols because we didn't have junctions. Maybe there's been new developments to help along then. There's also string net diagrams for symmetry enriched topological order. One way to do that is actually by first gauging the zero form symmetry, and that gives you just a topological order. You can construct the string net model, and then you can get the symmetry enriched topological order by ungauging. So for example, if you want to get Z2 enriched torque code, you condense the psi bar in the doubled Ising. So that's one approach that people have for constructing symmetry enriched string nets. String net models with enriched string net models with more general kinds of symmetry, like time reversal symmetry, etc. I think those are open problems. So they're not only kind of interesting for the purpose of simulating things that we don't know the answer to, like phase transitions, but they're also sometimes interesting for formal questions. So for example, Bowen probably knows more about this, but in this entanglement bootstrap program where people are trying to rigorously classify gap phases of matter, it turns out to be useful to try to map everything in one phase to the string net model of that phase, and then classify phases by enumerating kind of the fixed points in each phase. And as long as you can show that every phase with a gap boundary can then be mapped to a string net model, then you can just say, oh, we can classify things using string net models. So they're interesting for that, and they're also interesting for formal questions like what kind of lattice models can realize what kind of phases. So I mentioned that string net models can't realize phases with gapless boundaries. They realize phases that have gapable boundaries. But even if you don't have any chiral-centric powers, but you have like a Hall conductance that's non-zero, that can also prevent a string net realization. It prevents a commuting projector realization. So then asking questions like that, what kind of phases are easily simulable under certain assumptions, can help us maybe to understand the landscape of phases of matter more generally. Okay, thank you for your attention.
More questions? Lawrence, you look like you want to ask something. You want to ask something? Maybe in honor of Bowen, I'm going to ask, so you started to mention a little bit about chirality. Like, do you want to say a little bit more? I understand these models don't do something chiral. Is there something that people are thinking about from the lattice perspective to deal with these?
Yeah, so there are different approaches. There's one approach that tries to construct lattice models just starting from VOAs. There's one approach very recently that can construct, so there are, for example, topological orders that are non-chiral but still have non-gappable boundaries. Like if you had a U1 Simons theory with level 2 and -4. So this is the K matrix of your U1 Simons theory. This also has not any gappable boundary, even though the chiral center charge is clearly 0. And there's been some progress for constructing lattice models for these guys, basically by starting off with like a, it's similar to a Milan formalism and try to construct, but to my understanding, that's also not exactly solvable. So it's still has to use certain assumptions that, oh, we believe this Hamiltonian is gapped, etc. So in terms of exactly solvable models, I think probably string nets is all we have, or variants thereof. But yeah, it's an interesting problem to try to prove that more rigorously, because it was actually a lot of work to prove that, for example, commuting projector models can't realize phases with Hall conductance. And we believe the same to be true for phases that have non-trivial like thermal Hall conductance as well, because the thermal Hall conductance isn't observable. You can write it as an energy current, like a Hamiltonian term commutator. So it's kind of natural that if you have an energy current computed from commutators like then this has to be 0 for commuting projector Hamiltonians. But I don't know a direct way to prove that, for example, higher central charge obstructs commuting projector Hamiltonian. There's the argument I kind of briefly sketched that higher central charge might obstruct string net models, but we also don't know if all commuting projector Hamiltonians are equivalent to string net models. So there's some more subtle, like mathematical questions that haven't been completely understood in that respect.
Any more questions? Okay, so then, well, let's thank all the speakers and also Carolyn.